Okay, so actually my presentation comes at the right time because it might also talk a bit about reinforcement learning, because I think that deep learning and reinforcement learning are really on a path to even more synergy that we have seen than we have seen in the past. So this talk is different from the usual presentations you're getting here. It's not a tutorial. And it's not a talk about some work I did that I want to share with you. It's more about where I'd like to go and sharing my thoughts about that. So, of course, I'm going to talk about some ongoing work as well, but that's more the perspective that the whole thing has. Okay, so the starting point is, I think, what any researcher in their field should be doing, which is trying to look at the state of the art, what we have achieved, what works and what doesn't work, and compared to what? Compared to our goal in AI, which should be to bring machines to the level of intelligence of humans. After that, we'll see. But let's, we're far from that, and so in what ways are we far from that? In many ways, but maybe the most common critique about current machine learning is sample complexity. In other words, it looks like for many tasks, and especially if you think about a new task, say that a human would have to learn, or a child, or even an animal, the number of examples that are needed by the human, say a child, is much less than what is needed by current state-of-the-art systems. And so we need to understand why. And we need to move in that direction of being able to learn more efficiently somehow. Of course, machine learning is always about better generalization, and so we should strive for that anyways. Because the number of examples you need is directly connected to how well you're going to be doing in terms of generalization. Now, one reason why this is in addition to the usual thinking, not so obvious, is from the AI perspective, is that if you're an agent in the world, like a robot, you can't really have huge amounts of data like we might be able to do for ImageNet and things like that. You're going to be experiencing the data that you get from the little amount of lifetime that you have. And while you do that, you need to be making sure that you don't die, right? That you don't break yourself. And so the acquisition of data is expensive. Whether you're an animal or a human or you're a machine. Now, of course, for machines, we can do things like sharing data across lots of machines. But still, we'd like to know how come humans are able to pull it off and our machines are not. Currently, we're able to do with large amounts of data for training, for example, in reinforcement learning, because we have simulators or we have ways of producing large quantities of data. But if you take the perspective of an AI, like we would like to build a machine that is able to learn as well as a human, well, the learning agent doesn't have access to a model of the world from which it can generate as much data as it wants. So that works for playing Go or chess or things like this, like games in particular, but it doesn't work in most other settings where you don't have a good model of the world, and somehow maybe you're going to build one or you're going to do without it, but that's something to keep in mind. Now, going back to my own perspective on machine learning, and deep learning especially, which is centered on representations and the idea that deep learning is about learning high-level representations, really, at this point, we're not doing that great. So what works really well in industry is supervised learning, where the humans provide the high-level labels, right? We don't need to provide the representation at the top level of our ImageNet classifier, but the top hidden layer, but we have to provide the top outputs, targets, which essentially are telling the machine what are the important concepts that explain the data that humans care about. So we'd like to build machines that are more autonomous in their ability to discover by themselves those high-level concepts. Another aspect that's interesting to understand the limitations of current systems is to look at the kinds of errors they make. So if you only look at percentages of errors or accuracy, it may be misleading. For example, on ImageNet, you could conclude that current systems are as good as humans in terms of error rates. But the errors are very different. The errors made by humans are because, well, there are categories of dogs they don't know about. The errors made by machines are really stupid errors that like no like a 3-year-old would not make. So, and then if you look deeper, so for example, we had a paper last year on trying to see how these object classification systems are sensitive to aspects of the images that we don't care about. So we can play with the spectrum of the images, like playing with the high frequencies and the low frequencies in ways that, as far as the visual appearance is concerned, we can see a change, but it doesn't really make a big difference, and we still recognize those images, but those classifiers would fail terribly. And of course, all of the adversarial examples where you actually optimize for error reveal that the systems can be misled very easily. So in general, if you really look at these errors, and it's also very revealing in NLP when you look at the errors that happen, even though there may be few errors, the errors are not the kinds of errors that humans would make. They are errors which reveal that the system has a shallow understanding of the environment, that the systems don't actually understand how the physical world works, that the systems don't understand humans, don't understand society. And of course, we shouldn't be surprised, right? We train them on just a bunch of static images or a large corpus of texts. And as I'll try to explain, this is unlikely to work. And so finally, this idea that I proposed a long time ago in the early 2000s, that the goal of deep learning should be to learn representations which disentangle the underlying explanations, the underlying factors that explain the data, the causal explanations. We are very far from that. Again, this is something that's more of a dream right now. And even if we've made progress in unsupervised learning, generative models, GANs, we see that those systems capture interesting factors of variation, but it's still far from what we would like. Okay. So let me give you examples of things that I don't think are moving in the right direction and are not going to be sufficient to bring us towards human-level AI. So one example that I'll come back to, I think, is training natural language systems purely on text. And I'll give you arguments for why I believe this is not a good idea. Another example is generative models that are trained purely to generate sensory data, like images. You can produce very cute images, but I don't think that our own, say, imagination is happening in the same way. We are imagining not in pixel space, but we are imagining in an abstract space. So we need to figure out how we can do that kind of thing. Another example, which you find in some parts of our community, is let's build in a lot of prior knowledge. Of course, every machine learning system has prior knowledge because we have to. There's a theorem that's called no free lunch theorem, that there's no completely knowledge-free, no prior system that is universal. But we should strive, according to me, if we want to move fast towards AI, towards systems that use as little prior knowledge as is sufficient to solve the AI tasks. Why? Because that gives us more generality. Like, one problem we have currently in machine learning is that the systems we have are very focused. Like, you have a system that can play Go, but it doesn't do anything else. So we can do multitask learning and so on, but really, more fundamentally, we need to make sure that the principles we put in those systems are very generic and are going to work across a large set of tasks. Then we have to be careful when we look at the algorithms we choose that, at least on the face of what we are seeing, there's a chance for these algorithms to scale. Scale, like, our current neural nets are much smaller than the brain. Scale is in the sense that, the amount of data that we're trained on personally, or that the amount of pixels that we get, or the richness of the tasks that we're seeing. Currently, you know, our machine systems are working on a very, very small scale compared to what human brains are able to do. So we want to make sure that scaling is possible. So things like working with tabular representations, which has been the standard, for example, for many, many years in reinforcement learning, is not satisfying. And similarly, but maybe in a more subtle way, the idea of having distributed representations that has been so successful for deep learning, I think is not only successful, but is a requirement. If we drop that, then I don't think we'll be able to solve the kinds of AI problems we want to solve. Again, for theoretical reasons that have to do with the ability to deal with the curse of dimensionality. And then similarly, having representations that are not learned, I think is a no-go. So we can use some prior knowledge, but for the most part, the representations that are used should be discovered. If we have to handcraft the meaning of the representations, then I don't think it flies. We can probably put in some very abstract notions and representations, like I'm fine with having an algorithm that says, well, really we want the learner to capture a notion of object, and we're going to design the architecture so that, you know, it can do that. But that's very simple and doesn't require, you can think of it, how many bits do I need to specify my prior? If I need a lot of bits, then this is something concerning. There's a question up there. So I think people are interpreting the word disentangling in a way that's different from the one I have intended. I'll come back to that, but it's a very good question. And so the way I think about it is, even at the highest level, we should keep the ability to define new concepts in a combinatorial way that reuses the existing features or concepts that are there, right? And so I think that the main problem with a lot of the work that uses the keyword disentangling is they assume that the high-level features need to be strictly independent, right? And I think this is way too strong an assumption. But yeah, I'll come back to that, I think. So other examples of things we have to be careful is, in theory, it's often difficult to come up with theorems without introducing very strong assumptions. We have to be careful about these assumptions and strive to get rid of assumptions that are really going against our intuitions about what's needed. For example, I think we've reached a stage in machine learning where we have to drop the IID assumption that's so central to so much of learning theory. I already mentioned that we can't assume we have a perfect simulator. We can't assume things like, oh, we're going to be doing planning in sensory space, like pixel space, and the plan is going to unfold at a very fine time scale, like every 100 milliseconds. Because again, that's not going to fly for fairly obvious reasons in my mind. All right. So we're going to go through some of these topics, and I'm going to discuss ideas, that maybe allow us to go beyond these limitations. So let me start on language. And I said I believe that learning purely from text is not sufficient. So what's the alternative? Well, we want to couple text with other modalities, but more importantly, you have to think of it like it's not just multimodal thing. It's more fundamentally that we need to learn models of how the world works, as well as how to name these things with language, right? And just having the naming part is not sufficient. That's the message. And of course, when we want to train, we want to couple language with things like images and sensory perception, action, environments, whatever is necessary. Now, let me give you an argument why I think that learning only from text is not sufficient. So it's a thought experiment. Imagine you're an alien going to some planet, and you're going to try to understand the language of the aliens. You can actually observe the bits of information they're exchanging with each other. Now, that planet has some similarities with Earth, but also some differences. And on that planet, the communication channel is not noisy, so they can actually send bits perfectly through the communication channel, but they have to pay a high price for bandwidth, right? So they can only send a few bits at a time, and that means that they will want to compress the message. On Earth, things are a bit different. There is a lot of noise on the channel, and so in our communication, we introduce a lot of redundancy. Right? So it's standard sort of communication theory that I'm telling you here. And the other thing you should get from information theory is that if you compress a message optimally, say, what you get is a sequence of bits that look random. So now I'm the observer. I'm looking at those bits that are being exchanged between the two agents, and I just see random bits. I mean, they might as well flip bits and send those bits to each other, and I wouldn't see any difference. And that's a problem, because I'm doing something like language modeling, like we're doing in NLP, for example, which is like the basis of a lot of what we're doing. We wouldn't be able to learn anything. Okay, so what can we do if we're the observer on this planet? Well, we're going to have to do more work. Sorry, guys, okay? It's not enough to observe the bits that are exchanged between the agents. You have to observe other things. You have to understand their context so that you can potentially guess what their intentions are, and associate those bits with that context, and then suddenly you might be able to uncover what the language means. So that's what I'm proposing. I mean, I'm not the only one to propose this. It's been proposed a long time ago, but I'm saying, let's stop wasting time on trying to do a better job of language modeling or even machine translation or text classification, and let's focus on tasks where the learner needs to understand the environment that is being referred to by language, as well as how language is used to refer to meaning in that environment. Okay, that's a very simple message. And then you may ask questions like, should we first learn a world model and then learn a language model on top of it, or should we learn both together? I would rather go for the second solution, but there are many options. One of the things I want to mention of current work that we're doing in my group that's connected to this is what we call the BabyAI platform, and we have an iClear paper this year. So what we did in this paper and the corresponding work, which is online and you can play with, is build a platform for experimenting in an environment where there is very rich language that refers to actions and policies and rewards in a fairly simple environment that's very easy to simulate. So it's just a 2D grid world where the agent has partial visibility. So you can see in the image the grayed part is what the agent sees as input, and we see the rest, so we get context. The agent is the little triangle here, and it's given a mission, like put the blue key next to the green ball. And the missions are expressed in a natural-looking language that's produced by a grammar that's so very, very rich. It's not just a template thing. So you can get an almost infinite set of sentences using this grammar, 10 to the 19 instructions. And also, we have about 20 different levels, so different types of tasks, going from very simple ones, like go to one place, to more complex tasks where we have to move things around and go to places and do a number of things. Also, there's the question in these kinds of environments is, how are you going to train the system? From what signal, right? So you need a program that's going to provide rewards or demonstrations for the learner to figure out what to do. And for that, we need to associate with the language generation a sort of semantic description that can be, if you want, transferred into a Python code that's going to say, yes, the agent actually did the mission, succeeded in the mission, or can generate solutions to the, like demonstrations to solve the mission. The environment allows to play with the complexity of the world, like the number of rooms, and there can be complex dependencies between the actions. So for example, maybe you need keys to open doors and go through different rooms in order to get to the place you want and things like that. And yeah, so this is very, very early work, but what we found from this, what we found from this is even in such a simple environment, the current standard methods in reinforcement learning, imitation learning, which is basically supervised learning, require a lot of samples, like maybe 500,000 examples for a particular task, where you would think a human that has been maybe trained with the first few levels and then you give it a new variation would need maybe, you know, dozens of examples or something like that. And so we are far from the goal. But it's interesting to build these benchmarks so we can evaluate how much progress we make. And now the agent has the opportunity to discover the environment potentially through exploration and to build some sort of representation of how things work in that environment so that it can then figure out what those missions mean using very few examples. At least that's where we're going to go. And I think that to get there and to stay in the area of language, we need to not only develop the system 2 machine learning, because we as I said the other day, we've made a lot of progress on system 1, things like object recognition and perception, that can be fast, intuitive, and so on. On system 2, which is more like language related, and logical and sequential and so on, I think that we're not doing that great yet. But what we should not do is say, okay, we're just going to do system 2 and forget about system 1. This language grounding idea is basically that we need the two things together, right? We need the system 2 concepts to be deeply associated with the representation of the world that is built at the level of system 1. The other thing is something that I realized not so long ago. You know, I used to think that the logical explanation of the world is sort of this pristine, exact, and perfect representation of how things work in the world. But that's never going to happen, right? If you think about our linguistic communicated understanding of the world, it's very imperfect. It's very coarse. And it, you know, it requires very few bits to express information at that level, but at the same time, it doesn't capture all the subtleties, and that's why, you know, the intuitive part is necessary in our day-to-day life. So, so we should really think of this this high-level modeling of the world with something maybe like rules and logic and reasoning and planning as a very rough approximation of how things work in the world at the level that's communicable and with which you can reason, but it's not perfect, it's not exact, and it relies on system 1 to do a lot of the details. But we need that system 2 aspect. And I'll try to argue later when I talk about causality, because it allows us to do things like project ourselves in completely new situations that are unlike anything in the data. So that's basically called counterfactual reasoning. Even things that are contrary to the data can be imagined in this way. It's very hard to do that under system 1 things where, you know, well, if the model thinks that this is a 0 probability event, it's a 0 probability. We can't change that. But with system 2, the idea is we decompose the knowledge into reusable pieces that can be combined in new ways, even ways that have 0 probability. But like, well, we want to see what would happen if, okay? And this is useful because it allows us to, for example, imagine dangerous scenarios, right? These are very unlikely, but we need to be thinking about them, and we don't want to have to wait to experience them before we learn from them. All right, so this is like a very practical application of having a system 2 component. On the other hand, system 2 reasoning and planning is very slow, inefficient, and so as much as possible, anything we do with system 2, we try to convert it to system 1. We form habits. Initially, when you learn a new skill like driving, you do it with system 2, you follow the instructions and you try to follow the rules and so on. But then it just becomes a habit, you don't think about it, and it's very efficient. But when you get to a completely new situations, like you're driving in North America for most of your life, then you get it in London, and it's upside down, left and right. Like now you need to use your system 2, okay? Don't try to go with your habits. All right, so let me move. Okay, before I move to another subject, any question on like the language stuff? Because probably I won't touch it back. Okay, yeah.
So about system 2.
Yeah.
There are different logical models that.
Yeah, lots of people have been thinking about this problem for 60 years or something.
But should it be like 0, 1 or like fuzzy, like a probabilistic logic?
Well, so that's a very good question. So we clearly entertain discrete concepts in our mind, right? And language is using a lot of that. At the same time, we also have to carry some sort of uncertainty and maybe also notions of what we care about and what we don't care about. So some soft aspect is necessary, and the soft aspect may also be really important for learning, because we know that if we can do all the computations in a soft way, then we can do gradient descent, and it is really, really efficient. So if we can keep a lot of it, even though underlying we care about discrete concepts and continuous concepts, we manipulate both at the high level. The discrete concepts, maybe it'd be more convenient if we can manipulate them in a soft way, whether it's through probabilities or some other like soft attention, is a way to do that. All right, so let me say a few words about generative models that I mentioned in my little not to-do list. Let me cite Jeff Hinton here to motivate unsupervised learning. Unsupervised learning is one of these areas that we've been working a lot on in machine learning, but I don't think we've made clearly enough progress. Most of the industrial deployment of deep learning and machine learning in general is essentially using supervised learning. Okay, so what does Jeff say about unsupervised learning? He says the brain has about 10 to the 14 synapses, and we only live for about 10 to the 9 seconds. So we have a lot more parameters than data. This should be something we should be concerned about from a statistical perspective, right? Then he says, this motivates the idea that we must do a lot of unsupervised learning, since the perceptual input, including proprioception, is the only place where we can get 10 to the 5 dimensions of constraint per second. So what he's saying basically is that we have this huge capacity in our brain, and it's got to be because we want to extract information from a correspondingly large amount of data. And the only source of a high amount of data is coming if you consider actually modeling that. And so that's what unsupervised learning is really about. So that's I think an interesting thing. Practically, if you care about applications, not all the time, but in many cases, it's very easy to get unlabeled data, like just pure observation, whereas data that has a semantic label coming from humans or somebody who gives you rewards is expensive. Now, there's a word that my other friend, Yann Lequin, likes to use called self-supervised learning. So self-supervised learning, in his mind, means just a rewarding of unsupervised learning done right. Okay, so unsupervised learning includes things like he and I think are not that useful, like clustering. And so we want to focus on the aspects of unsupervised learning which give rise to learning interesting representations like distributed representations. And that means we need, the training signal is in the data itself, right? And a very simple idea that has come up, for example, in denoising autoencoders, is that we want to predict parts of the data given other parts of the data. And it turns out that this is actually a much more powerful principle than one might have thought of, say, 20 years ago, where everybody was focused on maximum likelihood is the thing to do. But actually, it turns out that we can learn really, really good representations using these kinds of principles. In fact, a lot of state-of-the-art in NLP these days is based on self-supervised learning, where you do things like predict a word given its context. It's like if I give you a sentence and I hide some information and you have to predict the hidden information given the things that are not predicted. And you can do it in many ways, of course, like current things like BERT and XLNet, and of course the old Word2Vec are all using this. Now, I would like to suggest that the general idea of self-supervised learning is good, but the part I don't like about it is that the current ways of doing this basically say, let's predict the parts of the data that we're hiding from the parts that we're not. But I'm not satisfied with that. I would rather like to do something like this, but in the latent space, right? Because I don't like the idea of predicting pixels. Like, I don't think that my brain is very good at predicting pixels. But my brain is very good at predicting high-level things, like what's going to happen at the end of this lecture. Somebody's going to come, a lot of people are going to come here and ask me questions. So that's like a high-level thing. I don't have like a video of this in my mind, right? But I have like an abstract thing that really captures the meaning, and I can almost visualize those people. But not quite. Like, I can't get the details, yeah? So we had a recent paper where, I mean, over the last year, we've been working in my group on estimators of mutual information, and now we're also working on entropy. But anyway, so all of these things are not just like theoretical constructs. They're actually very useful tools in machine learning. And in particular, they could be used to do something like self-supervised learning, but in latent space. So let me explain why this is useful. So first of all, if we don't do mutual information stuff and we just say, let's predict like the latent space at the next time step. Sorry, I'm tired. So let's predict, okay, xt plus 1, but not in pixel space, but in latent space, given the latent space at t, predict the latent space at t plus 1. Okay, it sounds like reasonable, right? In fact, I feel like that's what my brain is doing. It's predicting abstract stuff in the future, given abstract stuff now. Problem with that, if you take that as an objective function, and you backprop into the encoder that maps the low-level stuff to the abstract stuff, the encoder converges to a constant. Because you can see how that makes things easy to predict, right? So we get 0 prediction error, and everybody is happy except us. So how do we avoid that? So what happened when we maximize predictability at this level is that we don't control for the amount of information that is being transferred from the input to the latent space. And we need to control for that. We need to make sure that the entropy at the output of the encoder remains high and doesn't collapse. So there are many ways of doing that, but one is sort of explicitly estimating entropy or mutual information in one way or another to avoid this. Like, we can maximize the entropy of the output, or we can maximize mutual information between this guy, and it ends up being maximizing entropy as well. Okay. Yeah, so this is called actually deep infomax, and there are many variations of it. We had an iClear paper. A lot of that work was led by Devin Helm, but a bunch of other people in earlier work as well. And so it's a self-supervised learning strategy in latent space. And I think we need to think more about these kinds of do machine learning in latent space, right? Not so much in pixel space. Okay, now what we're going to be doing in latent space is trying to figure out how the world works. This is like a nice goal, but we need to be a little bit more specific. And I think the reason we want to do this, by opposition to just learning to classify or do the current unsupervised learning that we're doing, is to try to force the model to figure out not just the superficial aspects of things, but somehow, you know, this notion of disentangling was also like capturing the right high-level variables. That what are these variables? I think a very good guide is the words we use, right? So those high-level variables, they kind of correspond to the concepts that we manipulate in our thoughts. So if you look at the outputs of an encoder using current systems and you ask, well, what are they capturing? Do they capture the kinds of things we believe matter in the data? I think it's a good way to try to test yourself. Now, clearly, and I'll come back to that at the end of my presentation, there's a whole aspect about how the world works, which current machine learning is ignoring completely, and it's the causal aspect. I'll come back to that. Modeling the joint distribution of things is nice, but it doesn't capture the whole story. And for an agent in particular, it's really important to capture that causality aspect. Okay, so now I'm going to start moving towards an idea that will come back in various forms that I proposed a couple of years ago that I call the consciousness prior. So let's consider how we think. Let's consider how we plan. Let's consider what is it that we have in our mind consciously at a particular moment. It seems to be a very low-dimensional object, right? So what we have in mind at a particular moment is focused on selected aspects of the current state of the world. Like, we don't have, consciously at least, in our mind, a vision of everything that is going on around us. Instead, we have something very focused, right? Maybe you're paying attention to my words, or you're looking at a particular word on the screen. Maybe there's some ideas that I've evoked in your brain that is currently in your mind, and you're focusing on these few things at a particular moment, and then half a second later, it might be a different thing, right? And when we plan, like, think about, I'm planning, you know, what will happen next, what I will do next, and so on, and how I will go back to my hotel or whatever. When we kind of try to think about those plans we're forming in our head, we also focus on just a few aspects. We don't look at the full state of the world. Like, if I'm thinking about how I'm going to go back to the hotel, I think about, you know, am I going to take the train, and which stations maybe, do I have enough tickets? And so I'm focusing on just the few aspects of the world that I need to think about for reaching my goal. But then there's all of these other aspects of the world, like all of you guys and everything else going on in the world that I could think about, but they're not part of my plan. I don't even think about them, and I don't need to, like, simulate them, right? Okay, so this idea that thought and plans focus on a few aspects at a time is something that is currently missing in I think, our work in a lot, most of our work in machine learning and deep learning and RL. That makes life a little bit more complicated, because when we consider the more classical, say, modeling techniques, where we want to model in reinforcement learning, say, how the world evolves, how the state evolves from t to t plus 1, we actually try to capture the full next state given the full previous state. And when we plan in these methods, we typically think of how we unfold sequences of such states that cover everything in the world that matters, but not just to my particular plan, but to everything in general. So how do we have something that focuses on just a few elements at a time and train it so that, you know, what kind of objective should we use for this? It's not clear. And my intuition here is that the work that we've done in the last year or so on these information theoretical objectives may come to the risk queue, because what we want is, we want to focus on the few elements, but we want those elements to be informative. And it's not going to be sufficient. For example, for planning, we also want the plans to be useful for planning, like, you know, allowing us to evaluate how useful to me the final state is going to be. So there's going to be some, you know, multiple terms in the objective. This is all something we have to build up that we don't do right now. Okay, so I think I said these things already. So the this idea of a focused nugget, like pieces of information that I'm considering for my plan or my next thought changes a little bit the picture of the architecture that we should be building, right? So normally in current deep learning, we learn, say, a transformation from inputs to some high-level representation, and that's it. And now I'm saying, really, at the high level, we should be considering two kinds of states, two kinds of representations. The very fairly high-dimensional state, which would contain everything that your brain has access to, but that you're going to be selecting from a little bit of it to go into your conscious state. So your conscious state is going to be very, very small. The dimensions don't match. Like, so maybe think of it like your unconscious state has 1,000,000 dimensions, and your conscious state has 10 dimensions, right? So like really, really smaller. And we are using some sort of attention mechanism to decide what part of the large unconscious state becomes conscious at a particular moment. The other thing that's interesting about attention, and I think researchers in our field haven't yet completely realized this, there's something really powerful about attention which connects to notions in classical AI, and in a way, when you start thinking about attention, you have to think about indirect references, which is something very common in computer science and programming, something very common in like logic and so on with variables. So if you think about transformer architectures, for example, or self-attention or attention mechanisms, typically you have to introduce a notion of key and value, right? So you can think of the key as a name, right? But it's a discrete representation for a name. It's not a symbol. It's much more powerful. For a system that has this kind of attentive consciousness, this is important because if I put something in my conscious state, and then probably in short-term memory, and then potentially in long-term memory, I need to be able to retrieve it later. And so having something that plays a role of a name, or it's going to be a distributed representation for a name, allows me to retrieve it later. So now we have indirect reference, and we can do things like, well, I know the key, but I don't know the value. Like maybe I want to make let's say I want to make a prediction about the weather tomorrow. So I need to specify weather tomorrow in Edmonton. That's like a name. It's like a question. And the value might be, well, what's actually going to happen. So the name part is something that I need to be able to recover. Like tomorrow, I want to check if my prediction was good. So I need to see in my memory if I made a prediction about weather in Edmonton today. And so I need to be able to match names together. And that's sort of indirection. I need to it's like if when we put something in our conscious state, we are using the names to refer to things, whereas in normal neural nets, we don't have anything like a name. What we have that plays the roles of a name or a pointer, if you want, in neural net is just the ID of the neuron, right? So each neuron has a name, which is its position in the network. That's it, right? Whereas once you introduce a conscious state and attention, where you can say, oh, I'm going to take that information, I'm going to put it somewhere else. To know what this is about, I need to tag it with a name, and then I can use that for manipulation later. So this is a concept that we don't usually have in neural nets, but that's essential, I think, for system 2 processing. Okay, now so I kind of explained why I called it consciousness prior with the term consciousness, but I didn't explain why I called it a prior. The reason I call it a prior is that the reason I introduced this is I thought that by imposing this kind of sparsity of how many elements I'm allowed to manipulate at any time, I'm imposing a constraint, like a prior, on the representations that can be learned. Let me try to give you an example. So let's say I take this pointer and I'm going to say, or make a prediction that I'm going to be able to catch it. I got it. So when I made that prediction, I could have in my mind like a short sentence about, I will catch it in, in half a second or something. And that prediction was incredibly probable. Like the chances that I didn't catch it were pretty small. I could have made even safer prediction. I'd say it's going to fall on the table, and that's even more certain. So consider trying to make predictions in pixel space. It would be very, very difficult to make very, very certain predictions in pixel space. It's just the wrong space in which to make these very, very certain predictions. But in the space of abstract concepts, like the position of this object, like where it's lying compared to other objects, I can make very, very certain predictions. Like I'm very, very certain that tonight I'll be sleeping in the West End. I mean, something can happen, of course, but it's it's like probability 0.99 or something. Hopefully 0.999. But try to make such high probability predictions on pixels. It's not going to work. And so what's the difference? The difference is that I'm able to make those predictions using language, using concepts that are high-level concepts. And those high-level concepts have this property that you can make such very probable predictions involving very few elements. So when I make my prediction about the pen, I only need, it's funny, it's actually changing the slides too. I only need very few other concepts, like the position of this object and the sort of the geometry of my hand. But it's tiny compared to all the things that are happening at this moment. And so it's a very strong constraint that I'm putting on the high-level representation by saying, in that space, I am able to make probable predictions involving very few variables at a time. Okay, so it's a long discussion, but machine learning is very powerful, and it has a beautiful language to express these things. And you can express it by a single sentence. We can relate the joint probability among those high-level concepts is well captured by a sparse factor graph. Isn't that beautiful?
Different predictions may require different kinds of representation.
Yes, that's why you have a rich representation in your mind. Yes, and it's also combinatorial. I mean, language is combinatorial. So I can combine, I could talk about the blue pen in the red box and point to a particular prediction for that particular object. So we have this ability that's connected to the notion of disentangling earlier, right? We have this ability to construct new concepts by combining existing ones and create an incredibly rich set of predictions. But it's really important in what language, like in what space of representation we do that. And it's like an amazing property of the space of representation humans use that we're able to do these kind of consciousness prior predictions. So it's like the representation satisfies the prior. And the prior says the joint distribution can be captured by a graphical model that is very, very sparse. That's it, right? It's a very simple thing once you think about it in terms of probability in graphical models. So for those who don't know, a factor graph is just a way to think about a joint distribution by saying the joint over a bunch of variables is the product of a number of factors. Each factor links a subset of variables. So SK here is a subset of variables. And when I say that the graph is sparse, it means that there are few variables in each factor. That's it. All right. So any question on that part? I think there were several hands. Yeah.
From a computational point of view, it seems like being able
That's right, we are actually. You know the gorilla experiment? Oh, you should type gorilla attention in YouTube.
Try to have a system that is able to learn some sort of similarity comparison that allows it to think of two different things that in pixel space would be different as being fully similar from the point of view of
So the similarity space in latent space is going to be very different from pixel space, for sure. Now, whether we lose a lot of information when you go from pixel space to latent space, maybe, maybe not. I mean, your brain is really big, and it's bigger than the number of bits that come into your retina. So, we might keep a lot of information, but most of the time we use only a little part of it because of the consciousness bottleneck. I don't know. There were other hands. Yep.
Isn't this concept of having a larger latent variable similar to what we had a couple of years back as sparse autoencoders, but without attention part?
No, so in the sparse autoencoders, what we're saying is that, so let me go back to the previous, oops, wrong direction. Right, so in the sparse autoencoders, it would be like saying that this vector, the high-level representation, the unconscious, is sparse, right? And I'm not saying that it's sparse. Maybe it is, maybe it's not, okay? It's like an independent hypothesis. I'm just saying that we're going to pick a few elements of it in order to do our business. And our business might be planning, it might be conditioning the input, like in the gorilla experiment. Essentially what happens, I should have had it. There are a bunch of people that are playing with a ball, and you're asked to count how many passes are happening. And there's a gorilla that goes through them, and you don't see it because you're counting how many passes. All right, so your conscious state, because here you have like a mission, count how many times the ball is passed, is kind of making you blind to things that are happening in the input. Anyways, so yeah, it's different from just sparsity in the representation. I'm not saying the representation is sparse. Maybe it is, maybe it's not. It's like a different discussion. I'm just saying the joint distribution has a structure which is sparse. It's a different statement. There were a bunch of other hands, just I think completely in the back, yeah?
Regarding something that the sentence that you quoted from Jeff Hinton.
Yes.
Don't you think in that one we're ignoring the prior knowledge that we're getting from the genes, and probably came from like a million?
Oh, but there are not enough bits in your genes to specify that many synapses. So it's totally the wrong scale. No, but it doesn't know that much. So compared to how much you acquire in terms of experience in your lifetime, and compared to the number of synapses, what your genes are specifying is like peanuts. And someone in the back completely.
Do you also need to predict what factors are important in the next step that you want to predict? So
What characters? What do you mean?
There's like a few abstract concepts that we want to predict.
Yes.
What?
Yes, absolutely. That's right. So there's the attention mechanism not only picks, think about the planning that I was talking about, right? So not only picks what I'm going to be, what aspects of the world, what dimensions to look at in the current input. It also picks what aspects of the future that I'm going to be, maybe making a prediction or imagine, and ignoring the rest. So there's a kind of control mechanism which does the attention, which is very, very powerful, and in the case of planning, chooses just the right trajectory, abstract trajectory, which, it's amazing how we are able to plan with a single trajectory or two or three most of the time, whereas current planning is like, Monte Carlo research or whatever. We're going to be looking at hundreds of thousands of trajectories. No, it's a low-dimensional prediction. It's saying I'm only making a prediction about which, say, transportation mode I'm going to be using and a few details like this, and I'm ignoring most of the future, most of the aspects of the future. I'm only focusing on a few dimensions. That's the idea. There were other hands, sorry, yes.
How do we learn such a representation where we can say that each bit is kind of giving me a different information of the world?
What do you mean each bit is giving you a different information?
You said like if you block the remote, or you would know like what happens like when it falls on the hand. In the sense
Yes.
that you are abstracting away all the other information.
Right. So that's the attention mechanism. It's trained to focus on the interesting things. And it's trained. Like it's not like I don't think that it's designed to know ahead of time what's going to be important to predict. It's trained to know what to plan and what to imagine and what to pick. There was other hands, yes.
Would you say that system 2 is similar to, and I'm not sure how common this terminology is, go-fi, good old-fashioned AI?
Yeah.
Would you say that
Yes.
the way you're talking, yes, okay.
Yeah, so GoFi was trying to do system 2. And it failed for the most part because they were missing learning, they were missing handling of uncertainty, they were missing system 1, and they were missing distributed representations and probably other things. But they had some good ideas, and we shouldn't throw them in the garbage. All right, good. So now, let me move to agents. And of course, keeping representation as a central goal. Time is flying as usual. Okay, so disentangling. As I said, it's not about making the latent variables independent. It's about finding those high-level concepts which have those kinds of properties I've been talking about, and potentially other properties, right? So in general, it's sort of an ill-conditioned problem to find the right representation. There are many representations that could explain the data in the sense of likelihood. And so we need to put in some priors, right? Things like, some factors, some variables refer to things that are happening at different locations, at different spatial scales, at different temporal scales. So that's one kind of assumption, which sometimes we do exploit, and sometimes we should. When I talked about the consciousness prior, you can think of it more generally that once you map the data to this high-level representation, the joint distribution between those variables, including between the present and the past and the future, is simple. So things are much easier to model in the high-level space than in the pixel space. I think a lot of the models will do that, but keep in mind, this is the general statement we would like about disentangling. And finally, the thing that I'm going to speak more about in the next 17 minutes is that the kind of factors we think about at the high level, they have to do with our agency, our understanding of how the world works, how the world changes, what kind of mechanisms exist in the world that explain what we're seeing, and from the point of view of an agent, what are the aspects of the world that we can control? So let me go a little bit deeper into this. So there's a very old notion in psychology of affordances, and it has to do with the notion that the way we should really be, the way we actually think about objects in the world has more to do with how we manipulate them, how we control them, than say how they look like, their shape, and physical appearance or things like that. So we can actually put these ideas in machine learning. And one idea that I pushed a couple of years ago, and we're seeing more papers recently, is the notion of independently controllable factors, as we call it. So again, go back to this object that I dropped. It turns out that my statement about the object doesn't refer to the pixels, but it refers to the pen, whatever, the pointer, and it refers to attributes of the pen, like its position in space. So these things, like the position of this object, is something interesting, not just because I can make predictions about it, but also because I can control that position. Right? The fact that I can change that position very easily, whereas changing particular pixels in what I'm seeing without changing the others is very, very difficult. I mean, of course, you could use maybe paint and then change one pixel, but usually we can't do that. We much more easily control high-level concepts. And so it's another clue that we could use in forcing those representations to capture these factors to be disentangled, that many of them correspond to controllable aspects of the world. And you can, and these papers and more recent papers are looking at ways to do that by thinking in terms of, again, mutual information between the representations of the world, of the state, and representations of policies, trajectories, state and action trajectories and things like that. So the action part, or the intentions to perform particular actions on one hand, should be represented in a way that has sort of a bijection to how the world is represented. So at the extreme, you can think of it like, for each aspect of the world which is controllable, which might be like a dimension in my mind, there is a policy that I can build that allows me to change that dimension. Like I can change the x, y, z position of this object, and I have a policy that does that, right? If I have a policy for every such controllable aspect, well, clearly they are controllable, and I can do it easily and independently of other aspects of the world. Okay, and this is also, of course, connected to causality, which I'll come back to later. Yeah, so it's connected to also a notion of the different notions that are being explored in reinforcement learning, and if you want an unsupervised reinforcement learning, of intrinsic rewards. So things like learning how to control the world isn't something like solving a particular task. It's about discovering how the world works. And people have been proposing reward functions, where you can think of objective functions or terms in the objective function, which you could qualify as like unsupervised learning objectives for agents. And I think this is a very important research area which is growing, but I encourage more people to work in this. So there are different categories of these types of reward functions. I'm not going to go into much detail, but roughly things like what makes you curious, seeking novelty, seeking knowledge, not just surprise, because you could be surprised by something unpredictable, but you want something that currently you can't predict, but you might predict later after you've learned from it. Then the controllability empowerment, think about babies that are always trying to control their environment, controlling their parents. They're very successful. And things like an agent maybe trying to get rich. So what is it about? It's about trying to acquire as much freedom as possible so that maximize the number of things I could do later in my life. Right. So people have been proposing objective functions in that line. Okay. Now let me do a little parenthesis connecting to the sample complexity question I asked at the beginning on transfer learning and meta-learning. So meta-learning or learning to learn really is a very simple idea that is much more powerful than I think had been realized until recently, and still many people don't understand why, all that excitement. But I'm very excited, and I've been excited for since 1991. So, and at that time, our thinking was, well, so learning is sort of an inner loop of optimization, but really we should think about there's this outer loop, right, which is evolution. And how are the two loops interacting with each other? We shouldn't think of learning independently. And then when you start thinking about it, in even the lifetime of a human, there are multiple timescales of learning. So you have like very slow learning that may take years, like when you learn a skill, and then you have things that you learn over minutes, and then you have things that are just like controlled. So the way that I adapt my muscles to perform a particular action is also a kind of learning. I'm just finding the right configuration that optimizes grasping something. So there are many scales of optimization that are going on, and we need to understand how they interact. And basically, they're embedded into each other. And it looks like it's difficult to do optimization through optimization. But, you know, in the early 90s, we thought this was cute, but it wouldn't scale. And now we have the GPUs to do it. And okay, so why is it exciting? It's exciting because we can do things like learning to generalize. This is what you do when you do hyperparameter optimization. We can do things even better than learning to generalize. We can do things like learning to adapt quickly to a new task. That's the thing I was talking about at the beginning that currently we don't know how to do so well. And all the recent work in meta-learning is really focusing on this. Okay, so this is I think really cool stuff, and you should investigate it if you haven't. And I'm going to tell you one use of it. So yeah, I think we need to do learning theory to think about how we adapt to new distributions. So that means instead of thinking about a single distribution, we should think about multiple distributions, and how a learner will be exposed to these different distributions. And that, you know, then meta-learning is really useful tool to deal with that. And so we need to drop the IID hypothesis. And then in that light, I think there's a concept that has really had a strong influence on my thinking in machine learning that came through my discussions with Bernard Shopkoff, who wrote this book in 2017 with co-authors Peters and Jensing on causality, which I encourage you to read. And in this book, they describe a notion of independent mechanism. So what they're saying is that a reasonable assumption about the world around us is that it can be explained, at least at the level of our mental models, which are not like the true physics, right? At the level of our mental models, we explain the world as the combination of different mechanisms. So think about like the physics of light bouncing around and so on. And each mechanism can be described independently of the others. So knowing about one mechanism, like knowing about the shape of this object, doesn't tell me about the shape of this object. So there is a notion of independence which is different from the usual ones that I've been talking about up to now. And that can also be exploited to build better models. And I'm gonna try to tell you how we can do that. And yeah, so how we can do that, actually the idea is here in this slide, that when there are non-stationarities, when the world changes, when the distribution changes, we can assume that it involves very few of these mechanisms. So the world is explained by a huge set of mechanisms that are combined together to explain what we're seeing. So the mechanisms are different from the variables. They are more like how variables are transformed, right? And somebody does something in the world. That person is physically located in a place and a time. That action happens at a particular moment. Typically will only affect one mechanism, like the position of this object, say. And so we can exploit this assumption that the world changes in very localized ways. But the way we can exploit that is say, well, if that is happening, then if I had the right description of the mechanism, I should be able to adapt to those changes very quickly. Because if the change involves very few parameters and the other parameters don't need to change, that's the independent mechanism assumption, then learning is going to be very easy. Because I only need to figure out, infer, or learn a few things that have changed. But if I have the wrong representation, then I need to somehow explain a lot of things, a lot of changes, and it's going to be hard. Okay. So that sort of is connected to another really interesting topic in machine learning that came up in recent years, which is knowledge representation. So these are actually questions that GoFi people were asking. How do we modularize knowledge? Like, think of it breaking the representation of how the world works into small pieces, right? So these mechanisms that I've been talking about would like each mechanism to have a separate set of parameters. So we're looking at how do we modularize, how do we break a large amount of knowledge into small pieces so that each piece is kind of independent of the other, so that when a change happens in one of the pieces, it doesn't affect the other pieces. And yeah, so in current neural nets, the typical neural nets we use today that you've heard about, we don't have any kind of modularization. Every piece wants to participate in everything that happens in the world. And so when the data changes, when there's non-stationarities, when there's an intervention, when you go to a different task, you get things like catastrophic forgetting, poor transfer, you don't get very good continual learning, and so on. Things that humans are very good at, but currently machines are not. And I hypothesize it's because we haven't incorporated in our current neural nets this notion of modularization. That means that when something changes, we only need to modify a few things rather than changing lots of things that disturb a lot of the aspects of our mental picture. All right. So causality, I think is my last topic. It's important because specifying the joint distribution is not enough to understand how the world works. So understanding the world means understanding also how it could be different. It could have a different distribution. And the world is going to change because an agent, like a human, will do something to it. And we need to be able to figure out those changes. And that's what causality is about, understanding how the world changes due to agents. And so there's a language for that in which we say things like there's a cause and an effect. That means if I intervene on the cause, the effect will change. If I intervene on the effect, the cause doesn't change, right? So there's really an asymmetry here, which does not show up in the joint distribution. All right. So there's a lot of work in causality, most of it outside of machine learning, but there's one question in research in causality which hasn't been addressed, and I think this crowd and deep learning and reinforcement learning crowd can help to solve, and that is figure out what the causal variables are, right? So usually in the work in causality, people assume we know what the causal variables are. Like you're doing social science, and we observe the gender of a person and their job and their age and whether they have a particular disease, okay? So these variables are known. They have a high-level meaning. They're not like pixels. And they either tend to be causes or effects. But in the wrong space, there is no notion of cause and effect. Like if I have pixels, which pixel is cause and which pixel is effect? The question doesn't make any sense, right? We have to have the right representation. And that's a question that hasn't been solved yet, which I think we need to solve if we want to do AI. So we need to both discover the variables as well as their relationship. So when I was talking about the consciousness prior, it was about their relationship. And, but we need to jointly do that, and that's a hard job, but we have to do it. And I think we can use this trick of the independence of mechanisms to help us do that. So how is that? Well, if we have the right variables and we have the right causal structure that links them, then when something changes in the world due to an intervention, the time to adapt to that change will be small. Okay, but you could tell me, well, yeah, sure, but we don't have the right model and we don't have the right variables. However, we can measure the time for adaptation. And now if we can measure something, we can optimize it. This is what machine learning is all about, right? And so there's an experiment here where we consider how fast you would adapt if you had the right causal model, and basically, one of the curves correspond to having the right causal model, you adapt very fast. You have the wrong causal model, you don't. So we can turn that speed of adaptation as a training signal, potentially among others, in order to recover those variables. And in fact, we've been doing that. There is, so that the paper here just appeared on arXiv is on this topic. But there's a more general notion here that my friend Léon Bautou stated in a talk, I think, at ICML. He said, nature does not shuffle environments. We shouldn't. So what he meant is that the current practice in machine learning, when we have data, is to shuffle the order of examples to make them IID. But when we do that, we destroy information about the existence of non-stationarity, the existence of different sub-distributions that could tell a story about causality, and that is something we need to exploit. All right. Let me see if there are more questions, and then I'd like to say a few words about AI and society going beyond my time. So questions about causality and the things I've been talking about in the last few minutes. Yes?
So when you're talking about the catastrophic forgetting and learning new concept, can you think of something similar to the notion of consciousness that you have, where you have this key, and when the concept changes and you use the key to learn a specific thing, and when you need it, you use the key just to extract information related to that concept, and when you start to learn a new thing, you bring the new key and continue learning.
Yeah, I don't fully understand your question, but yes, there's a strong connection between the consciousness prior ideas and the causality ideas. But I think I'm going to move on to other questions. So, yes, just behind, yeah.
So in that paper about learning modularity, you say that if you can adapt quickly, then that means that you must have the right model structure. But could you also use other second order objectives? For example, you can say, you can also measure catastrophic interference.
Potentially, yeah. Yeah, yeah. Completely in the back.
So on slide 28, you mentioned about learning policies to control independent state variables. So is there any merit to say learn entire policies versus learning specific actions that can control independent state variables?
I didn't fully understand, sorry.
So on slide 28, you say that you want to learn policies that can control independent factors.
Yes.
In your state.
Yes.
So my question was, is there any merit to thinking about learning actions and not entire policies to like control?
Yeah, of course. It's not entire policies. I mean, you can think of like sub-policies or like specialized policies or goal condition policies, right? So you in reinforcement learning, you don't want to think about like a single policy that is the thing that the agent is learning. What you want is have a repertoire of things you can do. And then you can compose them in order to make more complicated things. And you want to be able, now that you have not just one policy, but like a family of policies, you need to represent them. And so we're going to have a distributed representation for policies as well. And you can think of those representations as intentions of the thing I would like to do. And so what you want is maximizing information between those representations and their effects in the state, in the right representation. I think there were also hands on the left. Yeah, in the back. The lady, yeah.
I have two questions. The first question, you said when we are doing meta-transfer learning,
Yeah.
so we need to have like good transfer environments to detect those causal changes.
Good transfer environments?
So when you said
Yeah, you need changes in the environment, and ideally they need to correspond to something realistic where like a few things change. You don't want to go from something like images and then suddenly you show sounds like this is not meaningful. But if you go from one room to another room, or you know that's a meaningful change.
but we are making an important assumption that it's an interactive environment rather than just
No, yeah, you're right. We want to go to exactly what you're saying. I mean, ultimately, the changes in the distribution are due to the agent, but they could also be due to another agent. So this slide that I skipped. So if you think about infants, it's interesting because they don't do much in the world, but they are apparently able to capture causality. And I suspect one reason is that they can infer a lot about causal structure by observing other agents doing things. There was another person, yes. No, it's never going to be full. It's never going to be complete. And yet, we need to be able to exploit it. Yeah?
we need to try different factorizations.
Sorry, what?
We need to try different factorizations to validate them. What if there are lots of variables?
Yeah, we need to optimize over factorizations. This is what we're trying to optimize. I'm going to move on because I'm already like 10 minutes late. And I wanted to say a few words about the ethical aspects of AI, because in the what next question, I think we have to think not just like what research we're going to be doing, but what's going to happen next. Due to our work, AI is going to be deployed in the world. It's already happening. And so that changes the game for us in the sense that it gives us a responsibility. And so when you work on something, you should ask yourself, does it fit my values? How is this technology potentially going to be used? Who's going to benefit from it? And maybe who's going to suffer from it? What kind of impact is it going to have? Is it going to have a large impact, not impact at all, positive one, negative one? So for example, personally, I don't want to work on military applications, and especially involving lethal autonomous weapons, these killer drones. I don't want to use machine learning to beat the stock market, because this is not bringing any value to society, just to some rich people. I don't want to increase the efficiency of advertising. I think advertising is, I'll have time, I think is psychological manipulation. I don't want to increase the efficiency of extracting oil and gas from the ground, because we need to keep it there. And you know, and I think we should reduce the meat industry, not make it more efficient. So these are just examples. So yeah, I mean, we should not, I mean, think about our values is good, but we should all like think forward, like what's going to happen, what is happening with our work. Issues of democracy, of surveillance, of security, because of you know, the military use, for example, with killer robots. By the way, killer drones are being built right now. I mean, we don't see them, but the science exists, and it's just going to happen. What we need to do is make sure that we minimize the potential use of them, and you know, encourage the international community to do the right things with respect to these kinds of questions. Often, maybe we're not going to be doing anything ourselves, but journalists are going to ask us questions. And I think we have a responsibility to think about those social aspects of how AI is going to be used. For example, the effect it might have on people who lose their job, and you know, how it might allow, say for example, with political advertising to really upset our democracies, how it might increase discrimination, how it might increase inequality and power concentration and things like this. So there's lots of issues. I'm not going to go through all of them, but I just want to tell you, it's not enough to study machine learning and AI. I think at this stage, not like 10 years ago or 20 years ago, you have a responsibility to be part of that discussion as experts in the field, and not just have, you know, focus on your equations and your code. All right, so I'm gonna stop here. And oh, Montreal Declaration. I have to say something about the Montreal Declaration. So I played a very small part in a big brainstorming that happened between not just AI experts, but a lot of people scholars from many horizons in the social and humanities, philosophers and legal experts and economists and healthcare people, to think about the kinds of guidelines and principles we would like to govern how AI is going to be used in our societies. And I encourage you to go to the website. There's like 100-page something, but you can look at the summary, which is organized around 10 principles, things like, you know, well-being, democracy, and diversity and prudence and things like that. And that's it. Thank you.